Okay, I think we're live. We should be live streaming live everywhere. Anka's going to remote mute the people that are not here. Admin. So, hey, I think we're live. We should be live streaming live everywhere. Hang on, I got a weird feedback here. Anka's going to remote mute the people that are not here. Admin. So, hey, I think we're live. YouTube. We should be live streaming live everywhere. Okay. My tech support Conrad's going to help here. So the idea is we're switching motion to admin. So, hey, I think we're live. We should be live streaming and go to the pods and talk to people there.
You should be good.
I should be good now, except I can't actually see my. Let's see. I got too many windows, so we'll find it. We'll find it.
Alt tab.
Oh, we've got to find the right one. There we go. Slideshow. Okay. No more homeworks except for the final project worksheets from this onward. Good.
For the first one, if students want to, they are free to change. Let's make that easier. So for the pods going forward from now, you have a choice to send your project PAs, like the pod or your regular pod. Just notify both to any case pod change.
I'm not sharing the slides.
I get it, like keep doing your thing.
There's one I got sharing screen. Okay. Next. Okay, I got it. Okay. Rubric coming for the final project. We're still working on the AWS credits. I got approved and it's still coming there. And we'll get the presentation date soon. And there's something in the chat. Okay, slides. Yes, thank you. Fixed. Bureaucratic questions, projects, information coming soon? This week. Okay, so today I wanted to do 3 things. I want to, in 5 seconds, review all of machine learning. We talked about supervised learning, right? Where you have classification or prediction for the first part, CNNs and things. We talked about unsupervised learning, where we did autoencoders and GANs and generative models, some of the transformers. And then we're going to talk today a little bit about reinforcement learning. I went and asked my friends in industry, where is reinforcement learning being used? And they go, it's really hot. We're hiring like mad. There's so much stuff with reinforcement. I said, really? What are you guys really doing? So we'll get there in a second. Conrad can think about what's he knows for people not playing AlphaGo. You'll talk about that maybe next time. Not game playing. I mean people in industry actually using these at Amazon and Facebook and places that actually do stuff. And I will pitch my version of reinforcement learning, which is a kind of automated decision making. Instead of trying to minimize a predictive accuracy, you're trying to actually optimize some decision to get some reward in the world, like how much money you make selling products or ads. We'll get there in a second. Then I'm going to digress. I wanted to show some really state-of-the-art what's happening, say, this month in large language models, which will be fun. Conrad could either have seen it or not. If you haven't read yesterday's publications, you'll get something new. And then Conrad's going to talk about how to write a paper and give us 10 rules for writing papers. Okay. Cool. Good. So automated decision making, right? We're doing reinforcement learning for the worksheets. I think there are 2 dimensions to think about reinforcement learning. The classic reinforcement learning, which you saw in 519 and 520, is online. You take a series of actions in the real world. You make a move, the world, here, put it and go, whatever, makes a move back and forth. It's online and it's sequential. You make a whole bunch of actions, and at the end of the game, you win or lose. Does that make sense? But note that life can be simpler. It can be simpler in the sense that either it's offline, you've got a whole bunch of data of states and actions from the past. And it could in fact be not sequential, but just one shot. The past doesn't matter, just do something now. So let's think about the offline version, the imitation learning. The dumbest thing I can do is watch the driver drive. Here's the state she was in. Here's the action she's done. Learn that. Does that work? You say no, but actually that's used a lot. Show me what the right thing is to do. And even for things like AlphaGo, the early versions of it started with a supervised learning set. Here's a bunch of games, and here's what the expert did. In this board position, mapped to an embedding, of course, this is the action the expert took. Make sense? So you can train a policy. Yep.
The sound seems to be like very, very far away for people.
Oh no, the sound is not going through the right system. Now it's probably right if I'm over here. Try that and see if it works if I stand here. I still haven't got this. Had Paul come in last time, we got it right. It's better, but that's not the one I wanted.
I'll mess a little.
So it's under the audio here. Okay, so that makes sense that the simplest version is offline, immediate. Here's the state, here's the action the person took. Take the right action. I feel like I'm very important. The other thing you can do for imitation learning is have something that's not just simple state action, but has a whole sequence of events you take, of actions you take, state action, state action, state action, reward.
Coda.
The data you've gotten by observing the world?
It's just this. No, it's this microphone now.
Yeah,
Because
it's even worse.
the microphones in here, they don't seem to actually work.
Well, okay, they did last time when we got the expert to do it, but I don't know how to do it. Okay. Okay. Okay, but I need to be able to go back in my.
Do you want me to get audiovisual help? Or do you want to use your microphone for the time being?
Both. Let's see. Let me
Okay,
get.
I'll call.
Okay. Hang on 1 second. Nope, that's one. There we go. Okay. So the one I want to talk about today, when I ask people in industry, what are you actually doing? What they're actually mostly doing is something that is online, in the sense that it's real exploration, take an action in the real world, show someone an ad or not, or a different ad, but it's immediate. There's no future discounted rewards. It's take an action, see the immediate response. And these are called contextual bandits. So that's what I want to focus on, is sort of contextual bandits. This is basically what I just said. So I've stolen slides from, yes.
Some people can't see the slides, sorry.
And okay. Technology is just amazing. So I've stolen slides from Amazon and Google because I wanted to sort of stress what reality is doing today. So here's an Amazon sort of picture. You've got a user. The user is the environment. You've got some features of the user. Where she is, where she's been browsing, history. That's your X. You feed this to an agent. That is your contextual model. Again, the context is the agent, what page person, what page they're on. The computer system takes some action as a function of the context, right? Following f of x is called a policy. They take the action. In a bandit, you have a whole bunch of different actions. Each action is called an arm. It's a choice. Pull this lever, this arm, this arm, this arm, this arm, take an action, and you get some sort of a feedback, like they click or they don't click the ad. So what are they currently doing? They're providing nice software that will learn some function that says, given a description of the state of the world, right? Someone in their browsing history, whatever we know about them, find the best action that maximizes the immediate reward. Right? This is a trivial version compared to playing Go or chess or something. We take a whole string of actions, but it's exactly the same idea. So you can also do the same thing. Google's also selling nice software that does it. And when you look at what they're doing is they say we're learning a Q function, which allows me to review what a Q function is. So what's a Q function? Q is you're in some state, some description of the world, you take some action. What's the expected value of the reward, right? The expected future discounted reward stream. But in this trivial contextual bandit world, the reward is immediate. You don't care about the future lifetime value of the customer. You say, hey, I show this ad, do they click or not? How many cents do I make off of them? Does that make sense? So they're using an epsilon greedy simple search and doing a very trivial optimization. So what does this look like in deep learning land? Deep Q learning. If you remember back to way when you took 519 or 520, Q function is updated by saying the Q value is some learning rate times the reward plus a discounted term gamma times what would be happen if you took the best one here. Paul, I still can't get the audio to work remotely. Even though we did all this last time and you helped me.
Okay.
So what do I want to pick here?
Go to audio settings.
We're there.
Actually, the one step at the top, try HDMI plus.
Okay.
When you're using this, does it have microphones and try
Yep.
test?
Testing. How are we doing remotely? Testing 1, 2, 3. Testing 1, 2, 3. Just 1, 2, 3.
Yep, sounds good.
Okay.
Fist bump.
Yes. Okay. Why we need a professional to pick the right thing, I don't know, but we did. Thank you. Go, Paul. Okay. Cool. So in classic Q learning, deep Q learning, what you're trying to do is minimize with your gradient descent the loss function, which is the reward plus discounted future reward minus the current Q value. So in standard deep Q learning, the kind that's used in most of the AlphaGo and all the modern game playing systems, your loss function is try and make the Q function, which is a deep network, right? Standard deep learning network, make the Q function move in the direction such that this thing goes to 0. Questions? This is the quick review of something that's been a year since you've seen it. And now the trivial version for a bandit, the bandit says, we don't care about the future. We're one step. Set gamma to 0. The future doesn't matter, period. And therefore, oh, we're not sharing screen again. Okay. So a contextual bandit says, hey, gamma is 0. Discount the future doesn't matter, we're one step. And all we're gonna do is say, hey, we're in some state, we take some action, try and make the Q value approximate an estimate of the reward. Learn the reward function. So it becomes sort of trivial, and it means that you can now learn it without playing 40 billion games. And it means that a company like Amazon that only has small data sets of people shopping can now use this as an optimization to learn to maximize a reward. Questions, comments? Okay, you're either happy or lost. Think about it, we'll go back. I want to then switch gears and talk about big functions. And I wanted to talk about a couple of things that have come out pretty recently. This one is submitted to archive on the 29th of March of this year. So this is the old one. Then we'll get to more modern updates. That's 29th of March was, oh yeah, it's like a week ago. So this is old stuff from a week ago. How do you train large language models? And if you look at sort of the history of large models in the old days, that would be 2020 to now, what you see is models like GPT-3 we talked about, 175 billion parameters, 300 billion training tokens. There are a bunch of these that people have trained. We're going to talk today about Gopher, which is the Google version of the OpenAI one. Lambda is very trendy right now. But they're big, right? 300 billion parameters. And you're limited by what? What? Data. Actually not, interestingly. Good guess, but wrong. Not limited by data. You're actually limited by compute power. How much GPU can you afford? Even if you're Google and OpenAI, you could say you might be limited because all you have is the whole web. But in fact, you could run it through a bunch of times, do permutations. Remember, we resample, we mask multiple times. So we're actually limited by compute power. And so the classic guys, that would be GPT-3 guys in 2020, figured out how to optimize this. But if you look at this paper that came out a week ago, what they show is a cool set of experiments done by the Google guys that says, here's the number of parameters, and here's the training loss, the thing I'm making small in my language model, and each line is an equal amount of compute time. The fancy word is isoflop, the same number of floating point operations. And you can see that for any amount of compute time, that if you increase the number of parameters, you get better accuracy for fixed time. And at some point, when you get more parameters in the model, you get worse for the same amount of compute time. Does that make sense? Why would more parameters be bad? Don't have enough time to do the gradient descent, right? If you get more compute time, going down, 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 you get lower loss. More compute time is better. Any indication they're saturating here? No, more compute time would be better. Why did they not go farther? Got too expensive, right? It's just Google. They have limited compute. Conrad, comments or things you're fixing?
I was just going to say, the important thing here is this is a log axis, not like.
Oh, this is a log axis, yes.
A log axis.
100 million up to 30 billion parameters.
There are 3 billion parameters. So that's a crazy number.
That is a pretty big number. Good point. And the key thing is that these things are roughly linear. If you get 10 times the compute power, you want to spend it with 10 times as many parameters and 10 times as much data. Right? The total compute is sort of parameters times data.
So, but the other thing that is interesting, it gets us from 3 to 2.2 at an extra cost of 1,000 times the compute.
Yeah, but it's 1,000 times the compute. So far, we're not totally maxing out Google. Who cares?
Sure, but
Hard to do that at home.
It shows that we have like, yes, no, and it's also exponentially spaced in the amount of compute.
Yeah.
So it basically means that we get less and less from more and more compute. Already.
Yeah, I think that's limited marginal returns. Everybody good on this? So what we want is the right ratio. So you can pick a fixed amount of compute, look at Gopher, which is the old style last year model, 280 billion parameters, 300 million tokens, and look at the modern one they did, Chinchilla, a fourth as many parameters, 4 times as much data. Same compute cost, right? Chinchilla is more accurate. And they've got 40 pages of running on everything in the world. So interesting question is, how did OpenAI, which did the preceding version, get the wrong ratio?
Well, they had no way of knowing what that ratio is. Now, this is the first paper looking at what the ratio
They
is.
didn't figure it out. And it turns out the fine print is there's always an annealing rate where you say, how fast do I change my learning rate? And OpenAI got it really wrong because the annealing rate depends upon how big your model is.
But this brings me to like a meta point here. When we do deep learning models, we often have a whole bunch of parameters, learning rates, annealing rates, compute amount, like all those things, and they're all coupled with one another.
Yeah,
So
really coupled.
The others matter. And if we think about it from an evolutionary perspective, this is something that makes the field slow. And we will undoubtedly see that in the future, they take out these degrees.
But at the moment, each time you change anything, you got to change everything else. Cool. So basically, the good news is that you can get much better performance without being much bigger, right? More compute time, compute longer with smaller models. But coming more recently, this would be April 4th, came out. When was April 4th? That was like yesterday. Okay, so up to date. Yesterday, Palm came out, and it's a big model trained on 6,000 chips, GPUs, so it's a lot of it is doing the massive parallelization, trained on all sorts of data. And here we see the number of model parameters, again, logarithmic, 10 to the 8th, 9th, 10th, 11th. Then we see some measure of how well it does across a big battery of tests. What you see is Gopher. That was the old style model here. In orange, what you see is this green dot, which is Chinchilla. That was the one I just showed you, which was the much smaller model, trained on much more data, third the size, 3 times as much data. And now you see the new one, Palm, with more and more parameters. And what you see here is the average human on these problems. We have superhuman performance. What we see here is the best humans. We're not anywhere near the best humans yet. So there's a big gap on these problems between sort of average and good and really good. And what we see is something that outperforms pretty much everything they've seen.
Okay, but to be fair, if we extrapolated the red curve, it would also get to where the blue curve is. Maybe it would just need 10 times the compute.
Yeah, but they don't have, it's more like 100 times the compute, and it's more than Google's willing to spend. Because we're now talking many, many millions of dollars, even at the price they're paying.
Right.
So these factors of 100 compute really add up.
But it feels like it's getting ugly in a way. Like
it is getting ugly.
Okay. That's all I wanted to say.
I agree. So what do they say? Once you have these big models, 500 billion parameters, it can do everything with one model. So we talked last time about fine-tuning for codecs, GPT-3. What we're seeing now is something which actually is trained on everything. 80% of it's English, 20% is other stuff. It's got GitHub and other stuff thrown in along the side. It's just everything. And it's remarkably good at a crap load of really general problems. It's not going to replace you and do your homework for you, but it's becoming closer to an all-purpose sort of thing. And I've got the link there. I won't take the time because I want to make sure we get to your.
But the question is what we mean with an all-purpose thing. Like this thing's being trained on like, what was it, like a couple trillion tokens or something.
Yeah.
So basically that thing has heard anything that a human has ever said.
Right.
So that means that despite the fact that there's so many things that it can do, it can mostly do them because they're basically the data set.
And the problem with that?
The problem with that is that, like, it's usually not last year's joke that we want to explain. It's the new joke that we want to explain.
It's pretty good at generalizing to explaining new jokes. So that's the interesting thing is that I haven't either. It's only been out for like 24 hours. So
how do you know it's good for new jokes? They had one good joke.
yeah.
Okay, here's the joke. Okay, hold on. It's about whales and pods, and now I forgot how it goes. This is very embarrassing. Okay, so
Keep talking. I'm going to find the
we
joke.
have two TPU pods. How do they communicate? Oh, there it is. Look at that. Did you see that Google just hired an eloquent whale for their TPU team? It shows them how to communicate between two different pods.
Boom chick.
It's such a bad joke, actually.
All the jokes on GPT-3 and Lambda and stuff are bad jokes, right?
Okay, fine.
But note that that's the input is explain this joke. You could also ask, is this joke funny? And the answer is maybe no, but okay.
Okay, but like it is one of the really simple jokes. It's a word replacement joke.
And it turns out with no specific training on it, it's able to note that a pod both means a group of whales and a bunch of 522 students. Oh wait, no, it's not the one they're doing, but
okay, but
group of TPUs.
But I'm not sure, like how hard this is. No, like the history of machine learning is doing things that people believe to be hard that we're not.
I don't think it's hard.
This isn't easy.
I agree it's easy, but I think that almost all human thought is not hard. People are not very smart. People mostly do stuff because they've seen it before. People always complain, all these things doing or memorizing, all it's done is read all of Wikipedia and all of GitHub. And I'm going, yeah, and if I could remember all of Wikipedia, I'd look really smart too.
Okay, but like people do much better on a much smaller amount of compute. And we're not scaling our compute to like factor 10 every year.
Whoa, we have similar compute. That's a hard one. I'm not sure when we should go there.
Okay, no one knows. People do have a lot of compute, but they certainly don't have a trillion tokens.
They don't see it. This is trained on more words than any of you have heard in your lifetime. If you run the numbers of you hear the whole life me talking at this speed, what a horrible thought. This is more words than you have heard in a lifetime, for sure. So it's trained on a lot more data.
You can say how many words do we hear in a day? Maybe 1,000 words?
No, 10,000.
10,000 words. Well, that's a lot of talking.
I talk a lot.
That would still be 3 million per year.
Yeah.
300 million hard upper limit. And they're
tiny amount, right?
They're training on factor 30,000 more. Like that.
Yeah. No, it's an incredibly inefficient, stupid algorithm, but it still works sort of impressively well. So,
okay.
Let's see, where was I? No, I want to come back to the lecture, and I want to switch gears. Actually, I think. And any comments on the large models, except to note that they're getting better with more training data without that much more compute power.
But let me say another thing here, Lyle, just to briefly come back to it.
We should switch.
No, so we are now at 300 billion parameters, although we can do better with 70 billion in some cases.
Yeah.
Can you run this model on your computer?
No, my computer's not very big. But people are working on scaling them down, on trying to do, as we said many times in this class, right? Finding the right solution is hard. Hang one second. Finding the solution is hard, but if you can find it, often you can distill down to a smaller model. Yes?
Does the ratio thing also apply to fine tuning? So for example, if I had lots of words, could I unfreeze more layers for
Good question. Could you unfreeze more layers for training with more data? Probably yes. So people haven't done a lot of experiments. Mostly fine tuning, you have small amounts of data and you don't do very much adjustment because your goal is to take these enormous models and then train on your crappy 1,000 labels. But I think if you had a crappy 10,000 labels, you could probably train more. Good point.
Cool, great.
Okay. projects. I want to switch and turn things over to you to talk about projects.
Wonderful.
And writing papers.
So I will briefly go through a paper that I wrote a couple of years ago.
And the link is in the slide.
And the link is on the slides without a doubt, and it's also easy to find. Googling is not, Google is your friend always. But much of what the projects are about is in a way you're running up to like write a little paper about it. So you will need all your skills, but you also need good ways of writing those papers. My experience with previous version of this class is that the papers generally are not always all that good. So we will be talking a little about how to write proper papers, because the goal to write proper papers in a way also drives the way we approach projects. No, they're deeply linked with one another. So I was a PhD student with Peter Koenig, who you can see on here. And my first scientific paper that I eventually got published took 3 years and well more than 100 iterations. And I know because was back in Microsoft Word, and every new iteration, I increased the counter of the file name. And it was like my first paper number 167.doc. And it was extremely frustrating. And then I joined as postdoc, the lab of Daniel Wolpert. Now, with Daniel Wolpert, the experience was entirely different. He was like, okay, do the research. And I did some research. And he's like, okay, sit down next to me. And then we wrote an abstract before I had even finished my research. And then it was very clear for me what my research was supposed to do because I've written the abstract. And then I wrote my draft. He looked at my figures, made some comments. And then he said, okay, now you sit next to me. And basically over the next 6 hours, he took my draft, which wasn't any better than the drafts that I had written with Peter Koenig, and he converted those drafts into a paper, and the first paper ended up in Nature. And it was super readable, and it was fun. It felt totally different. What I will try to explain in the next couple of minutes is kind of what that process is that Daniel Wolpert uses, that my lab now uses, but I think all of your projects will be much easier. You'll come up with good drafts much faster if you follow these ideas. And I should also say, it is written with Brad Mensch, who's one of the most successful grant writing consultants. So he does writing work as his business. It also for a long time was the most cited paper on all of Twitter. And then we get beat because the president of the United States wrote a scientific paper, and you just can't compete with the president of the United States. So let's go through the 10 central ideas. The first idea, and arguably the most important that I really want all of you to keep in mind, is every paper, every presentation should have one central idea. Now, there's exceptions. You can say in engineering, I did lots of tricks and kind of solved the problem. In which case, your central idea is I solved the problem. And then there's like, here's the list of all the tricks that I used for that. But the key is you want to have one central idea. Here's a few papers. Attention is all you need. Which field did that paper start? Transformers, yes. NLP is much older, but like, yes, it jump-started the field of transformers. And it had really only one idea, which is like, let's set up attention this way and tinker with it. And it worked very well. Or ResNet, like there's one idea. Let's add skip connections. All the rest, irrelevant or secondary relevance. If you have, or like Xavier He, here's how to initialize the neural network. Now, simple as that. Super useful and one idea. Now, if you have one idea, writing a paper, or for that matter, a project report, is super easy because the project report has a title. Or if you have one idea, that goes into the title of your project report. That is usually a little innovation you did somewhere. And if you think through your project, there hopefully is one place where you can say, here's an extra idea that I'm using, where you could say, Residual connection in the so-and-so network make it run faster, or domain-specific knowledge improves performance of something. You want to have a central, of all the ideas that you have, you want to advance one of the ideas and make it be the central contribution. And then everything else is just to make that central contribution, like be clearer, more beautiful, and so forth. And you see it all over the world that the papers that really have impact tend to have a specific central idea. That's what they're cited about. And let's talk about why it matters so much for writing. Imagine you have 3. You're really clever. You have 3 great ideas in one paper. What are you going to do? The title? Which of the 3 ideas do you choose? All 3 of them? Well, if you have all 3 of them, I don't know how to even make that into a title. But maybe even if that wasn't the problem, then you have to write an abstract. Are you going to write an abstract about 3 things? And like, you want to give me some background. Well, you give me some background for each of your 3 ideas? And then you want to have a conclusion. Will you give me the conclusion of each of your 3 ideas? No, it doesn't work. You need to choose one idea and make it be the central thing for the purpose of writing. Now, while you're engineers, you need to get all the things right. No, good transfer functions, good optimizers, good balance of compute and the number of parameters. We get all those things. But when it comes to writing, that's not an option. You have to have one thing that is basically the central point of what you're talking about.
I want to give one example of that. I see this a lot with my students. It's hard to write the intro. It's hard to write the background, unless you know the story. And a lot of my stuff is cool way to understand NLP methods for understanding substance use disorder.
Right.
And you can either write a paper on cool NLP methods with substance use disorder as an example, or you can write a paper on what we learned about addiction. And then, oh, and by the way, here's the NLP we used, but you can't write them in 2 papers. That's 2 ideas.
And here's how you can get extra mileage out of it, which is if you have multiple people collaborating doing a research project, one of your team members will write the substance abuse paper,
We'll write the NLP one.
and in the end, both of them get good jobs.
So much easier.
So yes, like 100%. So that's the first thing. The second one that is important is that you are writing for humans. And it sounds trivial when I say it, not like, duh, we're writing for humans. How boring is that? But if you then look at how a lot of people write, they make these complicated sentences with really long words that is all like the jargon of the field. But who's on the other side? You're on the other side. Not like the person who reads the paper is exactly the same as the person who writes it, just like in a different field. Now, ask yourself how you'd explain something to like one of your friends. You wouldn't use these long words. No, these long words have the goal of just showing that you're a member of the team. But in reality, no one understands them, or they're very hard to pass. People use passive tense. I'm more objective if I use passive tense. No, you're not more objective. It's just hard to understand you. So the person reading it, so the goal of the paper is to make it easy for the person on the other side to understand what you write. Here's an exercise that I always do with people. I get like a paragraph where even I, having worked in the field for a long time, have like real trouble understanding. And I'll ask the student writing it, how would you explain it to a friend? And they explain it beautifully. It's like, wow, I understand everything that the paragraph meant. But in the end, they purposefully write it down in a way that is impossible to understand for human beings. So it's not rightfully conceptualized as I write a paper for like the Almighty in the sky. And I need to show that I'm worthy of writing this paper. No, in reality, we are mostly affected by the curse of knowledge, which is for that paper that I do right now, even if it's just a class project, I might have spent 30 hours of it or something. So at that point of time, I know it better than anyone else. And so in that sense, what we really want to do there is consider that it's a student on the other side of the line, someone who might be our friend. And in that sense, don't shy away from using that kind of a language. So now that we established that, that we deal with humans, let's talk a little bit about human psychology. If I give you a list of words, and I ask you to learn by heart that list of words, which word are you going to understand best? Which word are you going to memorize best? The last one, yeah. You will be really good at that. There's another word that you often remember, which is the first word. Now, and if we would, as a function of, let's say, this is depth here of that list, if we plot the probability of recall as a function of depth, we'll get something roughly looking like that. So there's something special about the first. There's something special about the last. Let's talk about another aspect of humans. Humans have a very limited amount of memory. So that means you always want to use one word for one concept. Don't use multiple words because that like loads their memory where they need to commit that all to memory. Now, here's how I believe, based on that, stories should be told. You want to have one paragraph that deals with one thing. And then the paragraph needs to run like a story. Given that this is how humans work, there's a standard structure how stories are told by humans. If you read any Disney story, it in a way exploits that. Right at the beginning of the story, we meet the prince and the princess and all their proms. It exposes what the prom is. So we start, if you want, with the context. And then all these things unfold and the prince runs away and like, what do you know? All those things that happen in Disney stories. Stuff happens. That's the contents of the story. And then in the end, there's a conclusion that kind of wraps it up, that tells the reader what the outcome of that is. So we have the conclusion here. Okay, so this is the standard structure of human storytelling. Now, when it comes to writing, if we look at a given paragraph, no, if we look at the overall story, it always has that structure. Why? Because a paper, by agreement, starts with the introduction. I tell you what this is about. I tell you about the field. I tell you about what's missing. And then stuff happens. I show you my results. I show you my methods and so forth. And then in the end, we have a conclusion, which is, therefore, we have just shown you a set of methods that does the following thing. So this canonical structure of human stories is true at the level of the paper. But I want to argue it should be true within every paragraph. Oh yeah, and that brings me one more thing about humans. If you don't give me context, if you don't make something relevant for me, there's no way I will memorize it. It's just you need to tell me why I should care. If you don't tell me, I don't. And so this is true at the level of the overall paper, but in an individual paragraph, and we will go through the various sections, I argue that every paragraph should start with a sentence that basically sets the context. It's almost universally a question without a question mark. It says we need to make sure that our stuff converges. We want to be positive that our comparison metric is good. We need a comparison metric. We need an outcome metric. We need an algorithm for the following kind. That's the canonical structure of the first sentence. And then the sentence, then the body of the paragraph basically goes through that. In the introduction, it might be that you say, there is a field doing reinforcement learning. They use the following set of methods. Despite all that, there's the following stuff that's still missing here. And then it has a conclusion sentence. Therefore, in the introductions, the conclusions are of the nature, therefore, someone should write the paper I'm currently writing. in the results section, it could be, therefore we can be positive that our stuff is properly converged. And in between comes the contents. Now there are there exists a competing format of writing paragraphs in science. The first one is here, the contents, conclusion, triple C format. The other format is executive format. It looks like this, where you say conclusions, and you follow it up with why.
And I think there's a cultural difference. I think Americans, particularly for papers, we do the Wharton bottom line up top, give me the results faster. I think one thing, because you're from a lot of cultures, I do think there are differences historically from people in Germany and China seem to have had different ways. And I think Americans very much tend to go toward give me the conclusions up front, don't give me 5 pages of background.
They both exist.
Yeah.
I would say that when it comes to papers at the meta level, we're almost forced into this. You know, like we are expected to have an introduction, we're expected to have a discussion and or conclusion sentence, or like section.
But you can still give the conclusion and intro.
Yeah, and you do a little bit of that, yes. So in any case, those are the 2 styles. Choose whichever one is closest to your heart, but you want to be mindful and keep that throughout the paper. If you mix those 2 structures, you're going to confuse your readers. You're also going to confuse yourself. Like, because if there's different formats, the reader quickly get used to your style, way of writing. That means that they will not, that they will then look for the important things at the end, and here they don't get it. Or they'll look for the question at the beginning, and here they don't get it. Or they look for the conclusion here, and they don't get it. You want to be consistent and only have one form. So here's an example from a neuroscience paper. It sets a question to rule out the possibility of central or peripheral fatigue we compared and so forth. So that's the question there. Then comes some results in between. At the end comes, therefore, the MVCs are not affected by. So this is a typical CCC paragraph. Okay, my cursors are dead. Yes, okay, here. Okay, so the next one, the next rule is optimize logical flow. So the first thing is, if you zigzag in the logic of a paper, that is extremely difficult for humans because it forces them to basically get all the data from the stack, load it into working memory, and then go through the logic, commit it back to memory, and then later on you ask them to come back to that. So any idea that's in a paper should appear in one place and be exhaustively from all the different angles be illuminated. So when you write, you want to have all the things about the same factor in one place. And that is to avoid zigzag. So you don't want to come back. There's only one way of avoiding zigzag in practice, which is you must outline your paper before actually writing it. And as you'll be working with groups, make sure you take the outline and you iterate through that. The time you spend on the outline is nothing. Now, like the outline, we often write it in 3 minutes and then we start writing paragraphs. Writing paragraphs, if you know what goes where, is super easy. It's just you write down what obviously this paragraph is about, which you know from the outline. So you want to spend a lot of time on the outline because otherwise you will end up zigzagging.
I find that a lot of people don't like me, don't know how to write outlines, but everybody at Penn knows how to write talks. And the thing I like about writing an outline as a PowerPoint or Beamer search sort of thing is then you're actually thinking about the audience. You don't write an outline as if you're writing to some hypothetical abstract person. You're writing an outline as if you're talking to your friend. And so the talk notion, it doesn't have to be a beautiful talk, but the outline of here's the figures I would use to tell the story, here's the bullet points. Thinking of the outline as giving a talk forces what Conrad said before, which is to try and explain it to a human, as opposed to writing it to be impressive or lots and lots of background, which you really don't have time or space to give background that you wouldn't need to help understand.
But that's why collaboration is so cool. Now, like I might write an outline and I'd be like, Lyle, what do you think about that outline? And Lyle would be like, oh, what? Why? Oh,
why
come on. Like no one cares about it.
I don't want the history of attention.
But it's so important, the history of attention, and beautiful.
So cool. Write the book later.
but you see what we mean with that. It's like basically iterating, spend the time on it. The output will be so much better because so much of writing that I see, but in fact, even for professional computer science conferences, it's entirely unbalanced. They spend a lot of time on something that isn't even the central point of them. And those papers generally do better. So the second thing is use parallelism. If I have multiple ideas of the same kind, for example, I do my deep learning paper, and then it could be and I say it's because I use attention really clever. But I also use like residual connections, and I also use like, what do you know, like a creative learning rate schedule or something. I want to know which of them it is. The way I want to make the arguments is, it could be that it's the learning rate schedule, but it's not because I have that lesion experiment. It could be that it's the attention mechanism, which is not, and here's why. And so if I have multiple arguments of the same logic kind, I want to make it so that the text mirrors the logical kind of the argument. So if there's multiple arguments that are in parallel, use the same sentence structure if it's a set of sentences. Use the same paragraph structure if it's paragraphs. Everyone trains early on when you learn to write, in particular in foreign languages, to mix up the words and mix up the structures. And it's much more beautiful, much more beautiful. Not like use different words. It's like it just has this energy. If you do creative writing, you're constantly trained at that. Scientific writing is exactly the opposite. Don't surprise me. Use the same words for the same concept. Don't surprise me with the paragraphs. Don't make it that they go like in different directions with dialogue forms and all kinds of like other creative things. So like if you have 3 arguments, A, B, C for something, paragraph on A, paragraph on B, paragraph on C, they should look exactly the same way. And that again makes scientific writing difficult because you've so been trained to avoid those things. But for scientific writing, my only goal is that I explain it and you read it and it's easy afterwards. So I'm not trying to make you happy about the text. In fact, if you find the text boring but the content clear, success. No problem. No one ever has any problem with that. Okay, now let's go through some concrete applications. So the paragraph, so the abstract has the whole paper in one paragraph. And let's talk about the whole paper. Every abstract, and hold on, don't I have like a nice graphic for that? Yes, I do. So context in my slides is always blue, contents is always black, conclusion is always red. All abstracts, all good abstracts have this structure. They tell me right in the beginning the one question that this paper is about is. That might take multiple sentences, no? Because like my paper might be about something very arcane. I might first have to tell you like, yeah, deep learning is a thing and it's useful to solve NLP problems. And within the deep learning field, there is the following problem that I will now solve. But so the one question is basically you try and litigate what the real problem is that your paper is going to solve. And then you say what you do in that specific abstract. And then you tell them what you found. And then usually you tell them why it matters. There's a lot of deep learning papers that kind of don't, that end with results. I think it's not very good for human beings because like they're then confused at that point of time. Okay, so and let's talk a little bit about like the one question. Now, like, how do I convince you of there being a question? Oh, thanks so much. How do I convince you of that one question? It usually requires me to do somewhat of a funnel where I say, here's the big field. Within that big field, there's this set of prompts. For example, within NLP, we need transformers that actually work. Within transformers, we need to be concerned about the learning rates. Here we come up with a way of adapting the learning rate to the size of the batch that does that. So, but you basically have a funnel in the beginning that convinces the readers of the question. And that one is then followed by here we do, and this is what we find. And then it's usually using our mechanism in the future, we will be able to avoid like convergence problems coming from the learning rate not being adapted to the number of tokens we have accepted. Here's an example. Who knows this paper? Okay, this paper is Xavier initialization. Now let's look at how that looks like. One of the like countless papers cite that it appears that multi-neural networks were not successful at train. Since then, several algorithms have been shown to successfully train them. Okay, history of the deep learning field. It was post AlexNet, with experimental results showing the superiority of deeper versus less deep architectures. Okay. All these experimental results were obtained with new initialization or training algorithms. It basically says the field is booming. They're all initializing somehow, and so there's something happening in that field. Then comes like all that thing that they actually do. Based on these considerations, we propose a new initialization scheme that brings substantially faster convergence. That's kind of the conclusion that a reader should take away from it. And the readers did take it away from it because Xavier initialization is basically built into PyTorch in every imaginable way. That's just an example. Now, that is the first part about the abstract. Now let's talk about the introduction. The introduction, what's the emotional goal of the introduction? Now, I want you to be excited to read my paper. What is the technical goal of it? I want you to kind of be on the same page with me, to kind of like share an understanding of what the problems are and kind of be ready for the paper. So what the introduction usually does, and of course I have, no, it starts with looking at a big problem. In the Xavier paper, the big problem is like everyone's training neural networks. But within that big problem, there is this narrower problem, which is they all have to find a way of initializing things. And initializing is obviously a problem, which is the narrower problem with it. And yet narrower is the paper gap. Here we derive how far in ReLU networks we should initialize the weight. So that has the nice funnel shape. Funnel shape is the meta structure of introductions. You look at the big field, what's the problem? Medium field, what's the problem? That field, what's the problem within there? And then you have the gap statement. It's what is missing in the literature. That's the one thing that your paper solves. That can be a big thing if you're Xavier with your Schwabencher writing like a big paper that will end up being cited 100,000 times. That can be a totally small thing. Like here we show how to use support vector machines to find like false money from photographs or something. But you want to like give readers basically a reason to care about the specific application. And then at the end of the introduction, usually comes somewhat of a summary of what you find. Now you give away already what you will find. That often in machine learning papers has more so recently, there's a special section which says contributions of this paper, which says A, we're the first to show that, and B, we're the first that, and so on and so forth. For very engineering-oriented papers, it's often the big problem is solve a given problem, and then the contributions are to solve this problem. We like bring these ideas to bear on that. In any case, now let's zoom into the paragraphs. It turns out that the paragraph in the introduction isn't generic. All paragraphs in well-written introductions are the same structure. If I look into the paragraph that deals with what's the big problem in the field, I will have the microstructure where the paragraph starts with what people currently know. A lot of people are training neural networks because in computer vision, they are state of the art. Might have been a paper we would have written in 2016. Then, therefore, lots of people have worried about how to train those networks, followed by, therefore, it's because so many people work on training these networks, it's important to ask for how we can make the training be faster, something like that. And so in every paragraph kind of starts with something big, makes it smaller, at the end comes, and here's what the question is. And the last paragraph with the structure is the specific gap that your paper answers. And then usually at the end, you give away what your approach and what your results are.
So I think lots of people in this class are going to end up going to industry, not writing research papers.
Yeah, and the structure is slightly different. Explain how they do
I
it.
think the structure is really similar, except in a research paper, here's the closest research paper ever written, and here's how ours is better in this way and changes it. In an industry application, it's here's the thing that we're currently doing in our industry, in our company, and here's the improvement I made, and here's the problem we did that makes this problem go away or get smaller. So the structure is really similar, except it's even more important to focus on here's what we're doing now, we the company, as opposed to what the research world is doing, and here's the improvement I've gotten, and here's why it matters.
But let's also be clear about the importance of the gaps. That remains. No,
It's
like
exactly
the paragraph for the internal white paper that gets you like your promotion will be of every year we lose 10% of our customers because we make ridiculously bad recommendation. Here's the data. Therefore, we should improve that part. Deep learning has shown that they're doing better things. Therefore, we need to get into deep learning.
The companies I know don't write white papers anymore. They give PowerPoint presentations, and it's exactly the same structure that you have to be clearer and even clearer, so even your boss's boss can understand it rather than technical.
Cool. That's the nature of the introduction. These are also the introduction slides. I start my talk with litigating that my research in that company is going to improve the bottom. My code is going to improve the bottom line. Okay, next. Here comes the results section. The results section is basically just a set of logical steps. It usually starts with highlighting what the methods are. It then moves on to like the logic of what you do. We use the following data set. That's what we do with the data set. And here's the pre-processing. Here's how we like put it into the situation, and so on and so forth. Here's how we built the algorithm. Here's how we can prove that the algorithm is correct.
It's super helpful to do it in the same order that the data actually flows. It drives me crazy to have a paper that does the pre-processing and the paper after. Do it in the same order that the algorithm is going.
Yep.
It's obvious, but surprisingly often not done.
Yeah, also, for example, specifically for CS papers, I really like seeing the pseudocode of everything that happens, instead of just the pseudocode of like this tiny thing that's somewhere in the middle.
It's nice to have a flow chart, an NLP, increasingly a little picture at the very beginning. Here's what the data is, this data. Here's the core algorithm. Here's the extra supplemental information I build in to make my thing actually work better. Here's the output. One little picture that sort of shows the overall data flow of the process. And maybe in red, here's the thing we added into the box, the architecture.
That's right.
You can see it quickly and see what's going on.
And it's all about clarity. And it totally helps if you think about how you'd explain it to a friend, instead of if you think about it, how can my stuff look like a scientific paper? You don't want to copy the average scientific paper. Now, the microstructure of it is, let's ignore the method summary. Often you have that in the beginning, but like every paragraph basically says, what's the question? what's the problem that I need to solve? Now you can say, to be able to have joke understanding, we need to have a database of jokes. Therefore, we download from so-and-so the so-and-so data set, and it has the following properties. Conclusion, therefore, we are now set up to evaluate how good or bad we are at explaining jokes. And this question, what we do about it, answer to that, you want to have that in every paragraph. And almost all papers violate that, and that totally makes reading hard. Because it's often easy, you know, like you basically take the methods, all the PyTorch code that you run, and you write a sentence about it. That produces this random collection of sentences somewhere. It's not helpful. Cut it, put it into like what they mean, what they are for, so that you can guide people through it. Good, that brings us to the conclusion or discussion section. It's about criticism and future impact. I like to write my discussion sections like this. There are people who do it differently. But here what we do is we first summarize what we've done so far, which is this paper has tested this following hypothesis, or we implemented a system that solves the following engineering problem. Then any good paper should mention its limitations. It should say, we use the ResNet because it runs on Google Colab, and here's the reasons why we believe a transformer would be better. But unless someone sends us $1 million for a compute, we aren't going to be able to do that. That's why we go down that way. Or the ideal data set wasn't available. We used a different data set. So you want to basically be honest about the limitations that your paper has. And then usually you transition to what your paper has contributed. You know, like here we showed how we can push the limits. This is what we learned from that. And ultimately what our outputs will be useful for the general world. And like when you talk about limitations, you might often say, I talk about what the limitations are. I detail them, I make you understand what the limitations are, and then I sketch how someone could do it better. When you talk about strength, you can say what it's useful and like the difference that it made in the world. If you instead give a talk because you go to a company, these slides are basically, this is what we do for the bottom line. And instead of weaknesses, there's little reason to just say I'm weak. What you then rather want to say is, these are the opportunities for future growth for what I'm currently doing.
And often those are the same thing. So often what happens is you pick some subset. So in solving real world problems, you typically do a smaller subset of the data, a small set of products. We'll do these 100,000 products first, then we'll roll it out. We'll do it in English first, then we'll roll it out in 50 languages. So often there's lots of limitations that you have. How much will the data change year to year? Are there subgroups or sub-markets that are not being addressed? And are there people that may be pissed because you haven't done a good job making their preferences known? What are the things that could go wrong?
And here we see that Lyle was with Google for a while, because we first do it on first 100,000 products because we need to do something small first.
Well, one of the things you discover, which I started today by saying, is often the methods that work well on smaller data sets don't scale up as you change the size of the data. You have to change your annealing schedule, your architecture,
everything.
Lots of pieces, and that can be a limitation. So you want to be aware of those, and often you want to prototype ideally on something that captures where you're trying to go. But you never solve the whole problem.
Right.
It's good to be direct about it. People appreciate that.
Yep. Being open about weaknesses is like, it's also key for your personal growth. Cool. Now let's briefly talk about allocating time. Every single student ever, and in fact, every professor I ever co-wrote with, spends too little time at the outline stage. Now, why? Because the outline is hugely consequential. A lot of writing mistakes happen because as you write it, you realize, oh, I need a few more paragraphs there. Only that paragraph that you then introduced is a zigzag with the paragraph that's earlier. Once you're beyond the outline stage, it's very hard to see zigzag. So often when I get students' papers, I need to take their text replace every paragraph with a heading so that I now know what the outline is before I can say, okay, here's the zigzag that we can take out.
And when I'm outlining, I think often about the figure. What figure, what picture is going to show it, what bar graph, what chart. And if you notice, like I summarized several papers today, I stole their figures from them. Once you have the figures and you've thought about the message, I'm comparing A versus B versus C in what order, consistently across the whole thing. Now I've got the figure done. Flowing the text around the figure is not so hard. If you write the text first and then write the figure and discover, oh crap, when the figure looks weird, I did ACB, I should have done ABC or CBA. Once you think about the figure, often that nails lots of the rest of it.
Yeah, and
so again, the story. What did you
and they all touch on one another. Yeah. You know, like the abstract sets out the big arch of the story. The outline needs to match that abstract. The figures need to match the outline. Once you do the figures, you will almost always have to redo the outline. Once you redo the outline, it often leads to changes in the figures.
And it's fast to change bullet points. It's really slow to write pages of text and then throw them away and rewrite them. And I watched so many papers where people write pages and pages and throw the whole thing out.
All the time. And I should say that in our lab, we will very often just like have hand-drawn like sketches of how we want the figures to look like.
When I say figures, I don't mean beautiful polished ones, same idea. It's an outline of the figure, but with a detailed caption. What's the x-axis? What's the y-axis? What's the caption? What's the story? Why is the figure there?
And here's the bizarre thing. I think you should do that before doing your paper. Yeah. And let me make that point. So it takes a long time to code up something, but which figures, which things that you coded contributes meaningfully to your paper depends on the story you tell with the paper. So I always ask people in the lab to write the abstracts before they do any research. Just pretend everything works the way you want it to. And that then helps for the research that happens afterwards. It makes sure you don't do experiments that you don't need. Anything that's orthogonal to your main message, it will not make it into the paper. So why you waste your time with that?
I do the same thing. Students always write the abstract first as if it were done. Then when you go and actually run the data, sometimes you say, crap, it didn't work the way I hoped, and you have to go back and change it. But at least you have an idea of what you're trying to shoot for.
And sometimes it's hooray, it didn't look like we were expecting it to do. Like, we found something really cool here.
Yeah.
So it's also spend time on having a good title, spend time on having a good abstract. Why is this good time allocation? Well, if you do a paper, a lot of people will see your title. A lot of people will see your abstracts. It's very likely that Lyle and me will see all your abstract text and all your headings, and other students will read your abstracts. Page 6 of your, or however long it's supposed to be, the write-up, is going to be a relatively small number of people who will scrutinize it carefully. In any case, lastly, reuse, reduce, recycle. Basically, don't feel shy about kind of like restarting something, revisiting something you've done earlier. And that's my process for writing papers. Anka.
One thing that I had a couple of questions about was what is the difference between the abstract, the introduction, and the conclusion? Like how, because you kind of like summarize your work in all three of them. How do you make them different?
Yeah, okay. So in the abstract, you give away in like 200, 300 words, if it's a computer science thing, you give away the entire paper, which means that basically you will litigate what the paper is about and what the gap is in the literature. And you will say what you did and you will say what you mean. And it's all very, very compact. So the way to think about the abstract is basically the story of your paper in 200 words.
And many times I find students write it in 500 words, and then the first half of the abstract becomes the introduction, because they've given all the background in the abstract that needs to go in the introduction.
Yes.
Okay? So usually you're tightening the abstract and putting that more background in the introduction.
Right. And now The introduction, however, isn't at all a summary of what you do. So the body of the introduction, there's two things. It convinces you that there is a question. And the second one is it motivates you for that question. And then only at the end of it comes a short executive summary of what the paper does.
And often it tells you where the state of the art is. Here's what people are already doing at a level you can't say in an abstract.
Yeah, and those two, of course, super synergistic. Like if you tell me, you can't tell me what the open questions are unless you tell me what the literature does.
Right.
And at the same time, the literature defines what matters for my paper. So basically, in the introduction, you only usually have at the end contributions of this paper, A, B, C, D, E. That's very, very technical and much longer than we have it before, but it's much shorter than what will happen in the discussion, in the results section, which needs to talk about all the technical things that happen. So if we have the conclusions of this paper sections in the introduction, it's really just technically, what are the things that you added to the literature? And then we have the results section, which again summarizes everything you do, but in very, very long. It doesn't summarize it. It does the opposite of summarize. It's like
Presents it.
It presents it. That's where the stuff happens. And then in the discussion, you again look at the whole paper, but we don't look at the whole paper as in the way you do, let's say, in the contributions. You rather look at the whole paper based on where that leads you in the future.
That's both the limitations, which Conrad said, the future advance, why this matters, where this might be in 5 years, who's going to use it, why do I care at more detail.
Yeah, it goes beyond it, if you want. Discussion conclusions goes beyond where the paper is. And in that sense, there you have the differences. So when it comes to outlining, let's just be clear about like what I mean with outlining. Like, I have an outline where every paragraph in the final version is exactly one sentence. And usually for me personally, when I do it, there's an error in it, which is the question, this is what I want to convince you of by the end of that. Now, once I have that, then writing it is very easy. The stuff before the error becomes the first sentence, like with more words and more beautiful. The stuff after the arrow becomes the last sentence, of course, with more sentences and words and so forth. And then in between is the logic that basically links the question to what the conclusions of that paragraph. So I find that basically with that style, I can literally write complex papers within a couple of hours. Okay, that's after doing it many times.
Yeah. And we're about at half.
We are at any questions? Let me see.
Awesome. We're looking forward to seeing cool, exciting papers. We are on Slack and everything and talking to people.
Awesome. Great.